Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the sum of submodules, definitions. Let let M A belongs to delta be any family of submodules of an R module M. The submodule generated by union of M alpha belong to delta is called the sum of submodules M alpha and is denoted by summation of M alpha belongs to delta. Remark: summation of M alpha belongs to delta is the smallest submodules of an R modules M containing each submodules M alpha. Theorem: let M alpha such that alpha belongs to delta be a family of R submodules of an R module M, then summation of M alpha belongs to delta is equal to summation of xi finite so that xi belongs to Mi, where summation of xi denotes any finite sum of elements of Mi. I belongs to delta. Define T is equal to summation of xi such that xi belongs to Mi. As in theorem, we can prove that T is a submodules of M containing each M alpha, where alpha belongs to delta, and is the smallest submodules of an R module M containing each M alpha belongs to delta. Hence, T is equal to summation of M alpha to delta. Problem on submodules. Let V is equal to R cube be a vector space over the field R. X3 is equal to 1, 1, 1. Show that V is equal to Rx1 plus Rx2 plus Rx3. Solution: we know that Rx1, Rx2 and Rx3 are submodules of an R modules R cube. Note that every vector space is modules. Hence Rx1 plus Rx2 plus Rx3 is a submodule of R cube is equal to V. Hence Rx1 plus Rx2 plus Rx3 is a subset of V. Let X belongs to V, then ABC belongs to V is equal to R cube. Further, triplet ABC is equal to A minus B x1 plus B minus C x2 plus C x3 will imply that X is equal to ABC belongs to Rx1 plus Rx2 plus Rx3. By theorem, as ABC belongs to R, we get A minus B, B minus C belongs to R. Hence, A minus B x1 belongs to Rx1, B minus C x2 belongs to Rx2 and x3 belongs to Rx3. But this shows that V is subset of Rx1 plus Rx2 plus Rx3. Combining both these inclusion, we get V is equal to R cube is equal to Rx1 plus Rx2 plus Rx3. Next one, direct sum of submodules. Definition: let M be an R module. Let M1, M2 Mk be the submodules of the modules. Then the summation of I is equal to 1 to k is a direct sum if each element x belongs to summation of I is equal to 1 to k can be uniquely expressed as x is equal to x1 plus x2 plus plus xk, where xi belongs to mi for each I 1 less equal I less equal k. In this case, we write addition modulo summation of I is equal to 1 to k, where xi belongs to mi for each I 1 less equal I less equal k. In this case, we write addition modulo summation of mi is equal to m1 addition modulo m2 plus addition modulo addition modulo mk. Each mi is called the direct summand of the direct sum m1 addition modulo m2 addition modulo dash addition modulo mn. One more theorem. Let M be an R module. Let M is equal to M1 addition modulo M2. Then M1 is isomorphic to M by M2 and M2 is isomorphic to M by M1. Let M is equal to M1 addition modulo M2. Hence, any x belongs to M has a unique representations as x is equal to x1 plus x2, where x1 belongs to m1 and x2 belongs to m2. Define f from m to m1 by f of x is equal to x1, f of x1 plus x2 is equal to x1 for each x belongs to m. By the uniqueness of the expression, f is well-defined map. Let xy belongs to m and let x is equal to x1 plus x2 and y is equal to y1 plus y2, where x1 y1 belongs to m1, x2 y2 belongs to m2, be unique expression of x and y. F of x plus y is equal to f of x1 plus y1 plus x2 plus y2 is equal to f of x1 plus x2 plus y1 plus y2 is equal to x1 plus x2 is equal to f of x plus f of y. Thus, f of x plus y is equal to f of x plus f of y. Now, let x belongs to m and r belongs to r. Assume that x is equal to x1 plus x2, where x1 belongs to m1 and x2 belongs to m2. Rx is equal to r into x1 plus x2 is equal to rx1 plus rx2. As m1 and m2 are submodules of m, we get rx1 belongs to m1 and rx2 belongs to m2. Then, hence, by the definition of f of rx is equal to rx1 is equal to r into f of x. Thus, f of rx is equal to r into f of x for each r belongs to r and x belongs to x. For from 1 and 2, we get f is r homomorphism. Hence, by the fundamental theorem of homomorphism, M divides by kernel F is isomorphic to M1. Now, we want to find kernel F. Kernel f is equal to x belongs to m, so that f of x is equal to 0. That is x1 plus x2 belongs to m, so that f of x1 plus x2 is equal to 0. x1 belongs to m1, x2 belongs to m2 is equal to x1 plus x2 belongs to m1, so that x1 is equal to 0. x1 belongs to m1, x2 belongs to m1, m2 is equal to 0 plus x2 belongs to m1, x2 belongs to m2 is equal to m2. Thus kernel f is equal to m2. From 1 into we get m divide m2 is isomorphic to m1. Similarly, we can prove that m divides m1 is isomorphic to m2, and this completes the proof of the theorem, and so on.